Good morning, guys. This video is over Chapter 15, Polymer Processing. Administratively, today homework 3 is due, so please email that to me by the end of the day. You can use either my work or my personal email. Personal email is preferred. It saves me a step having to forward it to my personal email so that I can grade it on my iPad. And I'll have a new, another homework set for the rest of Callister posted probably tomorrow. It'll include the material through Friday, which is the end of what we'll be covering in Callister. We still have yet to cover composites, which will be tomorrow, and then corrosion on Friday. And then we will take a short break as we prepare for the midterm. For those class days, I'm going to cover some material out of a text by Ashby on material selection, which in addition to midterm Q&A will give us about a week or so to review all the material together and answer questions and prepare for the midterm. Okay, so I'm going to go ahead and share the Polymer notes. Oops, that's not it. Wrong one. Let's go ahead and share. Why is it doing that? Looks to me like it's sharing the syllabus, not the notes. Okay, that should be good. All right, so we're picking up today where we left off yesterday, talking about polymers, and I had sort of stopped at the end of chapter 14, talking about the structure. And before I go on to the characteristics, the mechanical properties, and the processing for polymers, yesterday I couldn't remember, when talking about diffusion, what this delta P was. And it's simple, right? It's just pressure. This is an analog, if you recall, to Fick's first law. In Fick's first law, it's the most natural to kind of consider a gas diffusing through a barrier. In that case, pressure or partial pressure makes sense. Here we're talking about a gas diffusing through a polymer barrier, which is relevant, say, for using like a food packaging material where you want to limit oxygen getting into the food, or water vapor, and so the permeability coefficient of that gas through that polymer film is important. But it's being driven here by a pressure differential, a partial pressure differential across that barrier, which is analogous to a concentration gradient that we saw in Fick's law. So that delta P is pressure. This P sub m is a permeability coefficient. Okay. And so, similar to some of the points that were made yesterday in the last video, we can recycle a lot of the concepts that we covered in metals for polymers. One of those common concepts is the use of stress strain to understand the mechanical properties. And so you can do a stress strain curve on a polymer sample just like you can a metal, right? You can fashion it into a dog bone, pull on it with a known stress, measure the strain, generate your tensile test your stress strain curve. And the test is similar, but the results are quite different. First of all, you see that the modulus axis here is not in gigapascals or hundreds of megapascals, but in tens of megapascals, right? So we're talking about moduli that are similar in form, but quite different in magnitude, in the order of, say, 100 times less. So as a class of materials, polymers are much weaker than metals, obviously. They also have a sensitivity to environmental conditions and the conditions under which you test them that are much more dramatic than metals as a class of materials. For instance, the temperature sensitivity is quite dramatic. If you compare the stress strain curves shown here, you go from a brittle material at 4 degrees Celsius to essentially I don't know, almost an elastomer or a very ductile material with a change of only about 55 degrees 55 degrees Celsius temperature change, right? So on the scale of metals, 50 degrees is hardly anything. But in polymers, right, you get a complete ductile to brittle transition over that narrow temperature range. And so the mechanical properties of polymers is very sensitive to temperature, and this is actually one of its primary drawbacks is that it does have this temperature sensitivity. So any application at elevated temperatures, polymers generally are not a good choice. Mechanically, polymers can also span, a wide range of moduli and strain behavior. So we saw here already that you can have quite ductile, and that would be for thermosets, which we'll talk about. I guess we already have somewhat. Thermosets are more brittle at lower temperatures. They're more brittle, higher molecular weight, and various side groups. You can make a material stiffer and more brittle. You also have more traditional tensile behavior here, albeit at lower stresses, where you would have an elastic region, a yield point, significant plastic deformation, and then fracture. You also have elastomeric, right? Where here we're looking at, and I want to point out the axis here, the strain. So normally we're talking about strain as, for metals, maybe 0.0 something. Remember, the yield point is defined as a 0.02%, right? So it's very small relative levels of strain. Here, we're not looking at 0.0 anything. We're looking at 3, 4. This is, times. Remember, strain is a ratio of delta L over L. So to have a strain of 4, right, you are elongating 4 times the length of the original. And so for an elastomer, you can see the modulus is very low, and the elongation is off the charts until fracture. And also see here that the elastomer gets stronger as it approaches fracture for reasons that we'll talk about later. Okay. As we can see, polymers have different mechanical properties, and since this class is focused on this processing structure properties performance relationship, right, we know that these mechanical properties ultimately go back to the structure and how the structure changes under stress, and which itself goes back to the processing parameters. And so to illustrate that, right, we show here, we have kind of a different deformation mechanism because we have a different structure due to different makeup and processing. And this particular case here, this case B of the tensile test, it behaves differently than metals in the fact that as it deforms, um, it actually the region of the tensile test that next starts the neck here at yielding actually gets stronger, right? Remember, if you recall, in metals, that neck became the weak point and had a reduced cross section and continued to deform and become more narrow, and eventually it fractured. Here, you can get very high levels of strain because in some polymer systems, as you are deforming this gauge section here, that actually strengthens the material to the point where it no longer becomes the weak point, despite it having a smaller cross section. And so what you see is at the neck, that becomes the strong point, and you get deformation at every point along your gauge section until you've essentially deformed the entire length, and then you get fracture. And this is because, as we'll see later on, that when you stretch a polymer, the sort of intertwined length of polymer chains, kind of the plate of cooked spaghetti mental model, you're pulling it and you're aligning those chains, which, like we see in crystalline regions, when the chains are aligned, the bonding between them is enhanced because you have more interactions amongst the same chain, and you're also aligning those fibers along their strong direction. Remember, along the chain, you have covalent bonds. In between chains, you only have van der Waals forces. So as you align the chain in the direction of the stress, you see that it is getting stronger. And that is a completely different mechanism from the strengthening of metals. Remember, in metals we want to we strengthen them by preventing them from deforming. In polymers, actually, it's the deformation. In metals, those dislocations that are formed during deformation impede the motion of other dislocations. In polymers, we see that it's actually a reorientation of the polymer chains relative to one another, not necessarily them impeding each other's motion. Mechanically, we also see some new interesting behavior in polymer systems that we haven't really seen before, and that is a pronounced time dependence on stress and strain, in the sense that, well, we have a new property we refer to as viscoelasticity, which itself has a strong temperature and rate dependence. And to describe it, we have this quantity called the relaxation modulus. And what this is essentially a time-dependent modulus where if you apply a constant strain, right? So you strain a material to a certain elongation, and then you just measure the stress as a function of time, what you will see is that that stress will decrease over time as the material relaxes. So the polymer chains in the material are able to, I guess, adjust and to remove that stress. So it kind of accommodates the strain that you have put it under. And the relaxation modulus, right, the ability of this time-dependent relaxation of the stress to occur is very temperature-dependent because it relies on the movement of these polymer chains to accommodate a given level of strain. And so this temperature dependence here kind of has a couple of different regimes. As you go up in temperature, right, polymers at lower temperatures are brittle and glassy, right, because there's not much thermal energy in the material, right. Those chains have a hard time moving with respect to one another to relax the strain, and so the modulus is relatively high. As you increase the temperature, right, polymers pass through various stages where they have more mobility of the polymer chains. So you have kind of this leathery stage where you have a drastic decrease in the relaxation modulus, and then transitioning to a rubbery, and then a kind of a very flowing regime as you go up in temperature. And I'd point out that these temperature changes here are not very wide, especially on the scale that we would think of with metals or ceramic materials. We also have viscoelastic creep. So this is another way, I guess, of thinking about viscoelasticity, in the sense that instead of holding the strain constant and looking at the decrease in stress over time, here we're actually holding the load constant and looking at the increase in strain over time. Here, instead of a relaxation modulus, we kind of think of this as a creep modulus, in the sense that if you remember back to our discussion of creep when we talked about metals, remember creep happened when we had a sustained load at high temperatures, and the high temperatures kind of creates the mobility for, say, a metal alloy that you may have in a polymer system at ambient temperature or much lower temperature, in the sense that you have a balance between strain and recovery, and so you see sort of a constant increase in the strain over a sustained load. And so this is less so for more crystalline materials, and I would say also, in addition to crystallinity, you're going to see a difference in the viscoelastic creep for polymer structures that have larger side groups, that R group in the polymer chemistry, also ones that have longer chains, right? Just basically anything that prevents those polymer chains from sliding with respect to one another is going to increase, or decrease rather, the viscoelastic creep. I want to, I guess, reiterate here that this viscoelastic behavior is dependent on temperature and time, right? I already talked about here with this figure the relaxation modulus varying by orders of magnitude over very narrow temperature ranges. But there's also a pronounced time dependence, which we see here in defining the relaxation modulus as a function of time, and also creep modulus as a function of time. And for an analogy or a direct experience, we've all, as kids, I'm sure, played with silly putty, and if you roll it into a ball and you throw it against the ground, it bounces back up to you like a super ball, right? But if you lay it on the table and let it sit there, right, it will basically ooze into a puddle or a pancake. And also, if you pull on it slowly, right, you can pull it out basically to a thread. And if you pull on it quickly, right, it'll basically snap. So silly putty is a polymer. It's an elastomer, and it gives you direct experience of the drastic dependence of the mechanical properties on the temporal application of the load. And okay, so polymers fail in a number of ways. One is to fracture, and we've seen here so far, if we go back, talk about how, especially at low temperatures, materials can be very brittle. This also happens when you cross-link the materials. So cross-linking basically locks together all of the polymer chains, and no longer can they move relative to one another to allow the deformation to occur, which causes them to be quite brittle. This also happens for non-cross-linked polymers at a low enough temperature. Just anything that prevents the polymer chains from moving with respect to one another will increase the brittleness of a polymer. I already covered here in this figure that they have a ductile to brittle transition. And the difference, so in this can occur over a very narrow temperature range, right? Anyone who's ever gone out in the snow and played with the say a plastic toy, or as a child or your own children, some sort of a truck or a shovel or something, have found, right, that it's much more likely to crack when cold um, than when it's not. So um, polymers have a ductile to brittle transition that we can actually observe in our everyday experience. In failure mode, polymer materials also exhibit a form of failure called crazing, and this is similar to the microvoids and the that occur in metals at fracture, where you have sort of small voids that grow and coalesce, leading up to fracture. We can also describe polymers with the same fracture toughness model that we used before. The only difference being that the actual values for fracture toughness will be about 2 orders of magnitude less than what we would see for metals. Conversely, impact strengths are low, right? It doesn't take much of an impact in order to break a plastic or a polymer. And we also see, so here we're seeing a lot of similarities. The metal mechanical properties also use see fatigue, similar to metals, just at a much lower stress. And in addition, you might, for polymers, there's also some additional mechanical properties, one of which is tear strength. So if you're forming a polymer into a film, for an application, say for food packaging or for covering, something else, what the resistance of that is to tearing is relevant. You can also do a hardness testing on polymer systems. Okay. So I talked a little bit about the necking and how you get a progressively stronger necking region, which just keeps the entire test section, keeps it deforming. You get large deformations of a test sample, and that's due to the deformation. And so if you think about the atomic structure of a polymer system, as we talked about in the last video, you have, especially for straight-chained simple polymers, you have regions of crystalline behavior where the polymer chains are able to lie in next to one another densely in a repeating pattern, right, to form a crystal. But because the chains are long and fold back and forth one another, you can't have a fully crystalline material because you have ends and kind of loops at the end of these crystalline regions, which form these amorphous regions. And so any polymer system is going to have crystalline and amorphous regions in varying amounts. And so when you first put a load on a material, right, the elastic response is essentially the stretching out and straightening of these amorphous regions, right? You haven't deformed the crystalline regions at all. And if you were to remove the load, right, they would stretch, or they would relax back to the way they were, right, and they would become, they would coil back up. As you transition, so once you've stretched them to their limit, right, then you start to yield the crystalline regions, and so you would get chain sliding, and these the chains would move relative to one another, which sounds a lot like slip in metal systems, so that they would elongate by this slipping mechanism in the direction of the applied force. Once they've reached the kind of the extent of that mechanism, then you actually get the crystalline regions fragmenting and aligning themselves along the the direction of the stress, right? So this is what we talk about when we talk about drawing, and you can see how the material will become much stronger in the direction of the applied force as it's drawn into a fiber, for instance, because you have all of these crystalline regions, and the direction of the polymer chain is along the direction of the applied force. And it would also weaken it in the transverse direction, because you see there's basically, there's nothing holding these together besides maybe, one set of van der Waals forces here, and even then the distance is probably larger, and that force falls off with distance rather rapidly, right? So there's very little that's holding it together in the transverse direction, and quite a bit that's holding it, that is resisting deformation, further deformation in the longitudinal direction. And so this drawing, this aligning of crystalline regions, greatly strengthens the material along that direction, which is very useful for forming a synthetic fiber. And so if you want, so this is the mechanism of deformation, and you want to strengthen a polymer system, right? Then the key is to prevent this from happening. And so you can do so by altering the chemistry of the polymer before you make it in a number of ways, right? First of all, if you have a longer polymer chain, right, a higher molecular weight, then they're more entangled. There are more covalent bonds that are holding these crystalline regions together, and less likely for them to fragment into these pieces, right? It would be obviously easier to fragment at the region where you have a transition from one polymer chain to another, right? And the amorphous regions will be more entangled, leading to a higher elastic modulus. You can also, if you tweak the chemistry, right, or the solidification conditions, you can encourage more crystalline regions, right? So a higher percentage of the polymer chains will be part of a crystal rather than the amorphous regions. So this gives you more van der Waals bonding and prevents and I guess delays the deformation of these crystals into these smaller units. And actually, drawing itself can enhance the crystallinity. You can see even the amorphous regions attain a degree of alignment as they are drawn, and you get more likeness of crystal direction and orientation as you draw. So you're kind of increasing the crystalline behavior, but only in the direction that you're applying the force, only the direction that you're drawing it. It also is going to be easier to deform and draw a fiber at a higher temperature, right? Because I have more thermal motion here, and if we go back to what we saw with the relaxation modulus, right, I'm going to be able to relax in response to that applied stress, or that applied strain, rather. And so it's easier to produce the drawing at an elevated temperature, but at an elevated temperature, right, they can move both ways, so they could easily go back. And so after you draw it, after you establish this crystallinity, similar to quenching a metal, right, you need to quench a polymer system to lock in this structure that you have created. An interesting difference here with polymers versus metal systems is that in metals, when you anneal, that is, when you raise the temperature of a metal part to a higher temperature, but not one that is going to return it to a different phase, i.e., back to austenite, say for steel. If you bring it up to a high enough temperature where the atoms can start to move a little bit more, but yet you haven't yet changed the phase and kind of reset the microstructure, the metal systems the atoms will move in such a way that they reduce the energy and heal dislocations and remove crystal lattice strain, and all of that leads to more ductility and less strength. But in polymer systems, annealing actually has the opposite effect, in that allowing these polymer chains to move about at a higher temperature more readily actually encourages them to line up and form crystalline regions. And these crystalline regions increase the stiffness of a material. So annealing a polymer actually has the opposite effect of annealing a metal. Okay, so for elastomers, which is a class of polymers that is characterized by very large deformations, these are made by forming crosslinks between adjacent polymer chains. And so these crosslinks essentially bind all of them into maybe one supermolecule, so to speak, because you have these chemical bonds that are making these large molecules essentially one. And what they do is they provide a tie that helps to reestablish the original structure. So if you draw an elastomer into, apply a stress, say to a rubber band, for instance, what you're doing is you're kind of uncoiling at a molecular level these bends and twists in the polymer chains. But because you have these crosslinks, once you remove the force, it remembers where it used to be, and those crosslinks help it to coil back up and to recover that strain, which allows you to have very high degrees of deformation that is elastic. And even though because you have these amorphous regions and low crystallinity, that the modulus is low, but you have very high multiples of strain, 1,000% or something. These crosslinks are generally formed through a process called vulcanization, where you would have an elastomer resin, and you would add, in many cases, sulfur, which forms a kind of a sulfur bridge from one polymer chain to its neighbor. Okay. What am I doing on time? 32. Okay, so the thermal behavior here in this next page. So crystalline polymers, as is typical of all crystals, have a defined melting point. And this is the temperature at which the crystal, you always, when you talk about melting, I always picture this tug of war between the random thermal energy in a crystal versus the bonding energy. And so when the bonding energy is winning, you have a crystal. When the thermal energy is winning, right, you have a melt. For a crystalline material, this is a defined point because basically every atom is in the exact same position. And so when one atom has enough energy to resist its bonding, then they all do. And so they're going to melt at a defined temperature, which is indicative of metal systems, crystalline systems, and also ceramic systems, and for polymer systems. So typically for crystalline, highly crystalline polymers, you'll see a more defined melting temperature, and for highly amorphous materials, you don't see this defined melting temperature. Instead, we define what we call a glass transition temperature, which ends up being kind of a range of temperatures over which the material experiences a transition from a stiff material to more of a rubbery state. And both melting temperature and glass transition temperature is dependent upon the molecular structure of the polymer. The melting temperature is going to depend on the the size of a crystal, right? So the larger the crystal, the higher and the more crystalline the material, the higher the melting temperature will be. Also, there is a time dependence here. If you heat up a material very quickly, and as you heat it more quickly, it looks like perhaps the melting temperature is changing. That's not true. There's generally a time lag due to the fact that polymers have low conductivity. So when you heat it really fast, you can change the outside environment, or at least the outer layers maybe of your material, but that heat needs to conduct into the interior. And because polymers generally are a low conductivity, low thermal conductivity material, that takes some time. And so it may look like you have reached a higher melting temperature, but that could be, and oftentimes is, because just because the temperature of your furnace that you're measuring is a higher temperature doesn't necessarily mean the temperature of the interior where it's melting is any different, but it can appear that way. Melting is also accommodated with a volume change or a phase change. Remember that as we are increasing the thermal energy, our atoms are vibrating more violently, and that is increasing the range of that vibration. If you think about it in kind of a simple harmonic oscillator picture, and especially once you have a phase change, a liquid, there's more space in between adjacent polymer chains, which allows them to be more mobile, but that extra space also increases the volume. So you can see here the specific volume, that is volume per mass, increases as a function of temperature, right? Leading up till these transition points, both glass transition and melting temperature, but even beyond, right? So as we're increasing the temperature, we are providing more energy for molecular vibration, which is going to space out those chains and lead to a volume increase. You can also move around this melting point by shifting that balance between bonding of the polymer chains and thermal energy. So if I want to move this melting temperature to higher temperatures, right, then I need to change the chemistry of my polymer to make it more attracted or more bound or more impeded, and that will require more thermal energy to overcome that chain hindrance, right? We call it. I used to think of it in chemistry classes as sort of adding like boat anchors, and you can kind of think of it that way, where if you can change the number of side groups or the size, right? So I'll have a larger or more side groups, or side groups that have a higher polarity and more hydrogen bonding character, right? Then they're going to essentially act like an anchor and hold their position relative to their neighboring polymer chains more strongly and require more thermal energy to disrupt. The same thing happens for adding double bonds to a polymer structure. So now that's a position in the polymer chain that can no longer freely rotate. So it adds to the stiffness and essentially becomes something else to be overcome by thermal energy. Same thing with molecular weight. A longer polymer chain is going to be more entangled with its neighbors, and then branching itself also. That's kind of a form of adding these side lobes or these side groups, these boat anchors, all of which increase the melting temperature or the glass transition temperature depending upon the crystalline nature of your polymer. The glass transition temperature is typically most pronounced in thermoplastic polymers, meaning ones that don't have cross-linking. And as you add more cross-linking, the glass transition temperature character tends to diminish to the point where it might actually appear to go away completely, because with many cross-links, it doesn't really matter how hot the material gets, how much energy is available for the chains to move with respect to one another. They're bonded in place, and so it never really goes rubbery. It just heats until you start to break those bonds, and the material burns up. Okay, there's a lot in this chapter, much of which covers different ways polymers are used and their properties, and gives a lot of trade names and applications and those sorts of things. And I don't want to take the time to go into that. Refer to the text for more information. But I just sort of list here all the polymer types that are covered in the text. And polymers are everywhere. They're used for lots of different things. And they provide, in a lot of cases, very different properties to our metals. Right? First of all, they're a lot cheaper, they're a lot lighter, they're resistant to corrosion, they have low thermal and electrical conductivity, and so those properties make them suitable for a whole slew of different uses. And the tailorability of the chemistry makes them appropriate for for a wide range of uses. So we already saw elastomers here are a category, right? If we want a lot of elongation, you can pick that. Synthetic fibers, as we draw polymers into a fiber, right? We strengthen it and can draw it into a very thin fiber. Which we can then use to make fabric. Polymers are the dominant way of coating other materials. So all paints and varnishes and enamels are polymer systems, and they dry and cure by a number of mechanisms, either by a chemical reaction between, say, part A and part B, or a water-based kind of dehydration reaction, as say a water-based one component paint is drying. Polymers are also adhesive, which provide a bond between materials, both a chemical, as the adhesive forms chemical bonds within itself, and mechanical, as that adhesive works its way into the surface, the kind of the nooks and crannies, the surface roughness of the parts that it's bonding. Polymers are also easy to form into just about any shape, and can easily form films, which gives us a lot of materials to use, cheap materials for packaging and for plastic bags. You can also form a foam. Oftentimes the chemical reaction forming the polymer itself will produce gas. And if you trap those gas bubbles, then you can form pores and voids inside of the polymer, which reduces its weight considerably and can increase its insulating value, those sorts of things. You can either have gas that's produced as a part of the chemical reaction, or actually dissolve the gas into the resin system, and then later draw that gas out under vacuum to create the bubbles. Polymers are also, they have high-tech uses here. We'll cover, so this ultra-high molecular weight polyethylene. Polyethylene spans the gamut from, LDPE, low-density polyethylene, to like mid-weight density to high density, to this ultra-high density and these ultra-high molecular weight. And so the difference between them is just the length of the polymer chains, right? In all cases, it's just a straight chain of carbon and hydrogen. But the longer the chains get, the larger the crystalline regions can be, and the more entangled they can be. And so you get stronger, stiffer polyethylene as you increase the molecular weight. Polymers also form the materials that are used in LCD screens, and the alignment of those polymer chains can affect the transmission of light, which is essentially how these are turned on and off. Okay, I'm running out of time here, so we'll talk about a little bit of processing. Again, this is a kind of a quick overview, and the goal here is to tie how these are processed to their chemical structure and the resulting properties. I talked a little bit already yesterday about the synthesis and processing. So when you're making a polymer, right, the key reaction here is the polymerization, right, the taking of the small molecules and linking them together to form a much longer carbon chain. This is done through one of two main ways. One is addition. This is polyethylene here as an example, where you have a free radical initiator molecule that essentially breaks open this double bond, and forms kind of a self-propagating free radical that continues to attack other ethene molecules and keeps going until you either run out of ethene or you have some sort of chain termination reaction where, say, two free radicals meet up, and then you have a chain that no longer has a free radical, no longer grows. You also have, in addition to addition reactions, condensation reactions. And so the name condensation comes from the fact that you are removing a small molecule, oftentimes water, from the reaction of the polymer units. So in this sense, in this example here, we have ethylene glycol and terephthalic acid, both of which have an OH group that reacts to form an oxygen linkage, and the H2O is removed with every new link that is made. Right, and so this would be an example of, say, a polymer that has a part A and a part B, where you have, say, equal numbers of part A molecules and part B molecules that are consumed in forming the polymer. Here, in, say, polyethylene, right, you need actually a relatively small number of these initiator molecules, because you're going to have hundreds or maybe thousands of these reactions, right, for each one of these molecules. Okay, and as you are polymerizing, or processing the polymer system, so you don't just have the polymer chains. Oftentimes, you add other molecules to modify the materials, modify the properties. Those would be fillers and plasticizers, stabilizers, colorants, flame retardants. So fillers can modify the the entanglement of adjacent chains as they sort of kind of get in the way. Sometimes all they do there is to increase the bulk. Right? Maybe you don't need the strength of the polymer, and so if you add some filler, then you can make it the right size and at a decreased cost, because not all of the material in the part is actually the polymer material. You can adjust the stiffness of a polymer system by adding a plasticizer. So this would be a molecule that squeezes its way into the material and kind of pushes those chains apart a little bit, increases the ability of them to slide with one another, with respect to one another, which can make it more flexible. Stabilizers, this is specifically, say, for oxidation or UV degradation. So if you put a molecule into the polymer that is there to absorb ultraviolet radiation, then it does so and protects the surrounding polymer matrix. So you don't have, say, yellowing or embrittlement as those UV photons from the sun are breaking down those bonds over time. Dye colorants, that would just be molecules that are not part of the polymer but just disperse and give it color. And then also flame retardants would be, say, molecules that decompose under heat to reduce the flammability of the material. Okay, the last ones are different ways of forming the material. A lot of these should look familiar from what we talked about with metals, right? So you can do a lot of the same operations, only you're going to need less heat, less pressure, because polymers as a class of materials are easier to form than metals, but you can use a lot of the same techniques, so these should look familiar. The two big categories of polymers have different types of processing, as you might expect. Thermoplastic, these have a melting or glass transition point and become liquid, and so those are quite easy to melt and remelt and only require heat and pressure. Thermosets are a curing, so you have a chemical reaction that is happening, and generally this can only be done once. For your thermoplastics, it's quite common to have compression or injection molding, where you would have, say, a metal mold that is heated, molten liquid polymer is injected, and then the mold is closed, and the polymer is going to fill the voids of the mold, and then you have your part. You can have kind of an open mold like this. You can have a closed mold with a passage for the molten polymer to fill. This would be similar to, say, the sand casting that we covered with the metals and ceramic materials. A little bit unique to polymer systems, you can actually have, in addition to like extrusion, which we saw with metals, you can have blow molding. I guess you see this a little bit in ceramics, say with the making of glass bottles, but is also used for the making of plastic bottles, where you would have kind of a gob of plastic or a kind of a bottle preform, heated, and then compressed air is used to blow that polymer and stretch that film to take the final shim of the bottle. And then also casting, right? Casting is more common for the thermosets, in the sense that you would mix the two together, pour it into a mold, and then let it sit for it to cure. Again, unique to polymers, you don't really see the drawing of metal. Well, I guess maybe for wires. So in the making of fibers and films here, for fibers, you have a process of spinning and drawing, which can be done either into some sort of a solvent bath, that would be wet spinning, or not, and dry spinning, where you have kind of the extrusion of fibers and into through a small orifice or a spinneret, and then having them drawn and cooled or solidified to form your fiber. This is one that I think is really cool, is the making of plastic bags or plastic films, where you have an extrusion type process, but the injection of air. So as you are extruding it, you're essentially blowing like a big polymer bubble, and as that air acts to expand and cool the film, and so quickly you can collapse the bubble without it sticking to itself, and then roll it into roll that up, and it just seems a very elegant way of creating those plastic films, which is just, this reminds me of watching like how it's made, and like the industrial process of doing all of this. It's just very interesting. So anyway, so I'm at 52 minutes, so I'm going to go ahead and stop. Again, my goal with this is for polymers to point out some of the differences and similarities against the other material systems, and also to tie it back as much as possible to the structure. Remember, we're always looking after this processing structure properties performance relationship. So tomorrow we'll talk about composites, Friday it's corrosion, and then we'll do some material selection while we prep for the midterm.